In this video, we shall look at a few review problems on Archimedes' principle. First, a brief introduction. Let's assume you have an object floating in a liquid, like that. Since this object is floating, the free body diagram would tell us that the weight of the object, which is its mass times gravitational acceleration, must be the same as an upward force called the buoyant force. Archimedes' principle puts a value on this buoyant force. It simply states the value of the buoyant force acting on this object is the same as the weight of the liquid displaced by this object. So weight of liquid displaced by this object. The magic word is the weight of the liquid. So how do you get the weight of the liquid displaced? It is the mass of that liquid displaced times gravitational acceleration, g. And the mass of the liquid displaced is the density of that liquid times the volume of the liquid displaced. In this case, it is the same as the volume of the object below that liquid surface. So that is that volume times gravitational acceleration. So this expression gives you the buoyant force acting on this object. Now let's see how to use these concepts in problems. Problem 1. A hollow sphere of inner radius 8 cm and outer radius 10 cm floats half submerged in a liquid. The liquid's density is 830 kg per cubic meter. What is the density of the material of which the sphere is made? And find the mass of the sphere. So that is the inner radius, and that is the outer radius. Now this sphere is hollow, so there is nothing in the middle of that sphere. It is solid only in that part of the sphere. So the free body diagram states the weight, which is mg of that sphere, equals the buoyant force that is acting upward, F sub b. Now first let's do the left hand side. The mass of the sphere is given by the density of that sphere times the volume of the sphere. And to this mass, when you times gravitational acceleration, you get the weight of that floating sphere. Now what about buoyancy? The buoyant force is given by the weight of the liquid displaced. So the mass of the liquid displaced times gravitational acceleration. So the mass of the liquid displaced is the density of that liquid times the volume of the liquid displaced. That means the volume of the liquid displaced is due to the volume of that sphere below that liquid surface. So let's call it V sub L times gravitational acceleration. And you see that g will go away. Now let's calculate the left hand side. The density of the material is what we want to determine in part A. The volume of the sphere is due to the solid part of that sphere, and that is given by 4/3 pi the outer radius cube minus the inner radius cube. So this expression represents the volume of that hollow sphere. The outer radius is 10 cm, the inner radius is 8 cm, so let's put that in. Note I've converted the cm into meter. Now the right hand side, the density of the liquid is given as 830 kg per cubic meter. The volume of the liquid displaced is due to this entire part of that sphere, and that is given by, since half of it is fully submerged, and that volume of that entire sphere is given by 4/3 0.1 cube, because that is the outer radius cube. We note that in calculating the volume of liquid displaced, we have to include the entire volume of that sphere, as if the sphere is solid and not hollow. hence we don't subtract the inner radius cube as we did on the left hand side. So equating both sides, you see the 4/3 pi will go away, and we can solve for the density of the material that makes up the hollow sphere, and will turn out to be 850 kg per cubic meter. So that is the answer for part A. Now, having found the density, we can determine the mass of the sphere. The mass of the sphere is the density of the sphere times the volume of that hollow sphere. The density of the sphere is 850 as we have determined. The volume of that hollow sphere is 4/3 pi 0.1 cube minus 0.08 cube, which will give you about 1.74 kg, and that solves the problem. Problem 2. A block of density 900 kg per cubic meter floats in a liquid of density 1150 kg per cubic meter. Find the height little l, which is below that liquid surface. Free body diagram states the weight of that block equals the buoyant force, which is going upward from the liquid on the block. Now let's assume the top flat surface of this block is a meter squared. So the left hand side of this equation, namely the weight of the block, equals the density of that block times the volume of the block times the gravitational acceleration. The density of the block is given to be 900 kg per cubic meter. The volume of that entire block is given by that surface area of the top surface times the height of that block in meters, so it's 0.08 meter. So let's write that here, a times 0.08 and times that with acceleration of gravity equals, now let's calculate the buoyant force. The buoyant force is given by the mass of the liquid displaced. So the mass of the liquid displaced is the density of the liquid, which is 1150 kg per cubic meter, times the volume of the liquid displaced. And the volume of the liquid displaced is the same as the volume of the object that is below that liquid surface. And that is simply the surface area of that top flat surface times that little L. And to that we have to multiply the gravitational acceleration to get the weight of the liquid displaced. So A goes away, G goes away, and we can solve for L, which will turn out to be 0.063 meter or 6.3 centimeters. That solves the problem. Problem 3. A hollow iron sphere is almost completely submerged in water as shown in this figure. Its outer radius is 35 cm, so that means that distance right there is 35 centimeters. The density of iron is 7,900 kg per cubic meter. Find the sphere's inner radius, that means that distance. So let's call the inner radius R sub I, and outer radius is known to be 35 cm. So as we have mentioned before, the free body diagram states the weight of that iron sphere is given by its mass times gravitational acceleration, and it's floating because the weight is balanced by the buoyant force due to that liquid acting upward on the hollow iron sphere. Let's call it F sub B. So equating the two forces, you get that. The mass of that hollow iron sphere is given by the density of that iron times the volume of that hollow sphere, and to get the weight, you multiply that with gravitational acceleration. Now keep in mind, this volume of that hollow iron sphere is due to that part of that sphere. And we can easily calculate that. It is quite simply 4/3 pi, the outer radius, which is 35 cm, turn that into meter, so 0.35 meter cube, minus the inner radius cube, r sub I cube. And the way we arrive at this expression is by taking the volume of the bigger sphere with radius 35 cm minus the volume of the smaller sphere with radius r sub I. Now let's see how to determine the buoyant force. The buoyant force is defined by Archimedes' principle as the weight of the liquid displaced by that object. So it is the mass of the liquid displaced times gravitational acceleration. The mass of the liquid displaced is given by the density of that liquid and the volume of the entire sphere that is displacing that liquid. And in this case, the volume is the volume defined by that outer radius. So putting everything together, and don't forget the gravitational acceleration. So now putting everything together, equating the left-hand side to the right-hand side, we get the density of iron is 7,900 kg per cubic meter. The volume of that hollow iron sphere is given by that expression. So it's 4/3 pi 0.35 cube minus r sub I cube g equals the right-hand side, which is the density of the liquid, and we know it's water, so the density of water is 1,000 kg per cubic meter. V naught is the volume of that sphere as defined by the outer radius, so that is 4/3 pi 0.35 cube times the gravitational acceleration. So you see g goes away, the 4/3 pi goes away like that, and we can solve for r sub I, which will be 0.33 meter, or in cm, 33 centimeters. And that solves the problem. Thank you for watching.